Hey everyone, welcome back to Edgeverse. Imagine a computer that doesn't just crunch numbers faster. It thinks in ways that bend reality itself. A machine that could crack codes in seconds that would take today's supercomputers billions of years. It's quantum computing, and it's happening right now. Today, we're diving into this mind-blowing tech that's set to revolutionize everything from medicine to AI. Stick around. You'll see why this is the next big digital frontier. Let's start at the beginning. Quantum computing isn't some overnight sensation. It's been brewing for decades. In the 1980s, physicist Richard Feynman had this wild idea. Classical computers struggle with quantum physics. He proposed building a computer that runs on quantum rules. That sparked the field. Then, David Deutsch formalized it, showing quantum machines could do things classical ones couldn't. But the real game changer? In 1994, Peter Shor dropped an algorithm that could factor huge numbers super fast, threatening all our encryption. And Love Grover followed up with a quicker search algorithm for big databases. Early quantum computers, like IBM's 7-qubit setup, factored 15 into 3 and 5. Trivial math, but huge proof it works. Now, we're in the NSQ era, noisy intermediate-scale quantum. Devices with hundreds of qubits, but they're still glitchy. So, what makes quantum so special? Let's break it down simply. A regular computer bit is either 0 or 1, like a light switch on or off. A qubit? It's quantum magic. Thanks to superposition, it can be 0, 1, or both at once. It's like a spinning coin, heads and tails until you look. Mathematically, it's alpha times 0 plus beta times 1, with probabilities adding to 100%. For multiple qubits, the power explodes. 3 qubits hold all 8 combos at once. 300 qubits? More states than atoms in the universe. Then there's entanglement. Einstein called it spooky action at a distance. Link 2 qubits, and their states are tied, no matter the distance. Measure 1, the other instantly snaps into place. This isn't faster than light cheating, it's just how quantum works. Together, superposition and entanglement let quantum computers explore massive problem spaces in parallel. Classical computers? They're hitting walls. Moore's law is dying. Problems like simulating molecules or optimizing routes blow up exponentially. Classical machines can't handle it. Quantum? Born for it. So why should you care? Because the applications are game changers. First up, drug discovery. Finding new meds is a billion-dollar gamble, taking years of trial and error. Quantum computers could simulate molecules perfectly, no approximations. Imagine designing a drug that fits a cancer protein like a glove, or tailoring meds to your DNA. Time slashed from years to months, cost plummeting. Next, materials science. We could engineer stuff like room temperature superconductors, zero-resistance wires for efficient power grids, maglev trains everywhere. Or better catalysts for clean energy, super batteries for EVs, or solar cells that grab more sunlight. It's materials by design, not blind luck. And don't get me started on AI. Quantum machine learning could turbocharge it. Optimization algorithms like QAA solve tough problems faster. Think better financial models, risk assessments, or supply chain tweaks. Quantum neural networks might spot patterns we miss, needing less data. Logistics giants like Amazon could optimize routes in real time, saving fuel and time. Could this lead to super smart AI? Absolutely. Now, who's building this stuff? It's a full-on quantum arms race. Tech giants are leading. Google claimed quantum supremacy in 2019 with their 53-qubit Sycamore chip. IBM's pushing qubit counts, like their 433-qubit Osprey, and they offer cloud access. Microsoft? Betting on topological qubits, super stable, but tricky. Startups like IonQ use trapped ions, while PsiQuantum goes photonic. Governments are in too. US with the National Quantum Initiative, China's pouring billions, EU's quantum flagship. Universities like MIT and Caltech are innovation hubs. But it's not all smooth. Challenges? Huge. Decoherence is the big bad. Qubits lose their quantum mojo from noise like heat or vibrations. They need near absolute zero temps. Scaling. We need thousands, maybe millions of qubits, all connected without errors. Error correction? It's like spreading one good qubit across hundreds of flaky ones. Massive overhead. We're in NSQ, useful for experiments, but not fault-tolerant yet. Recent wins include better coherence times and gate accuracies over 99.9%. A full sure-run machine is probably a decade away. Transitioning gears, what does a quantum world look like? It's double-edged. Cybersecurity is the big one. Q-Day, when quantum breaks RSA encryption, could expose everything: banks, secrets, blockchains. Harvest now, decrypt later attacks are real threats. But solutions? Post-quantum crypto, new algorithms NIST is standardizing. And quantum key distribution uses quantum rules to share keys securely. If someone's spying, you know. Optimization wins. Quantum could perfect global logistics, cutting emissions, fine-tune finance for stable markets, manage smart grids for renewables. But ethics? This arms race could spike tensions. Who gets the edge first? Inequality. Only rich nations or core might afford it, widening gaps. Quantum AI could amp up surveillance or autonomous weapons. Scary stuff. Jobs. New ones in quantum tech, but some might vanish. What do you think? Will quantum unite us or divide us? We need global talks now on ethics and access. Wrapping this up, quantum computing isn't distant hype, it's emerging reality. From Feynman's spark to today's NISQ machines, it's about superposition and entanglement unlocking impossible problems. Medicine, materials, AI, all transformed. Challenges like decoherence persist, but progress is real. We're on the cusp of a quantum age that redefines knowledge. If this blew your mind, hit that like button, subscribe for more tech deep dives, and drop a comment. What's the quantum app you're most excited for? Check the description for resources like Quantum Computing for Everyone book or IBM's Qiskit courses. Thanks for watching. See you next time.